This is the robotic arm I've been working on. I've used it in several other videos, but here I have incorporated lots of features with this, and I'll go into great detail more on each of the features, but it's a 6 degrees of freedom robotic arm. It has a servo gear motor, gearbox for the shoulder, and then some servos, 1, 2, 3 servos for the elbow, wrist, and gripper. The gripper actually moves the camera. There's also a pixy camera that does recognition of this little red puck you see in front. There's a servo in the base that pans, and then there's an electromagnet that picks up the puck, and there's a switch I've devised that triggers an interrupt that causes the servo to the robotic arm to lift and move the puck somewhere else. So I'll go into some detail on the project here and the code. This is the breadboard that I use to wire the robotic arm and all the components connected to it. There's a battery pack that is used to energize the electromagnet. There's a relay that connects the battery pack to the magnet and triggers when a certain condition is met. A certain pin is set high. There's an LED that lets me know that the magnet is energized. I have some wings on this that allow me to actually anchor the wires so they don't pull out. The breadboard is larger, and I've used a separate power supply up in the upper right-hand corner. There's a negative and a positive alligator clips to supply power to this. I also have right above the Arduino Mega a separate little power supply that you can see there that's red that powers the servo gearbox. So I'll go into this too. So here the robotic arm is in the home position. The camera would normally scan this field here anywhere to find the red object. You can see that the pixy camera is picking up the object in the computer in the background. And now it's did the pan function to get it lined up. And now it's adjusting. It's going to do a level to bring the magnet right above the red object. And now the magnet is also energized, and it goes up. And I probably don't need to do this second lift here. I'm beginning to think I probably should just comment that out. And the second level, I don't think that's really necessary. Now it's going to do the while true. It's going to continue to go down, down, down until that magnet trips the interrupt. And it picks up the puck, the red object, and then does something with it. I just drop it back down. And then it goes back to the home position and will rescan the surface of the field from the home position. That's the position it's in now. The pan takes a long time. I probably could speed it up and have it do different speeds, but this project has already taken longer than I really want. So just wanted to kind of show you how it works. This is a close-up of the magnet with a heatsink and the trip switch I made for the interrupt. And it's kind of clever what I did here. And I'm apologizing about the steady cam I'm doing here. It's not too good of a job, but I'm using one hand to hold the camera and one hand to describe what I'm doing, so I'll do my best. Basically, there's a metal bar here, and it's connected to the robot arm. And I've soldered right here a little pin. You can kind of see the pin there. I don't know if I'm getting a good picture of it, but it's right there. And that is on this bar right there. This nylon nut insulates
this washer that I've anchored with this nut in the hole in the back of the magnet, and I'm going to remove the heatsink. Here's the heatsink, it just snaps on. And what happens is, as soon as this nut here touches this bar, you'll see another pin there. So between this pin and that pin, as soon as they touch, it creates a closed circuit and an interrupt occurs. And until then, this kind of just hangs down, bounces around as this moves around, and there's enough distance between here and here so that it never creates an interrupt. In addition to that, I also detach interrupts, so that helps keep the bouncing around as this arm flails around with the camera here. This is the camera back here. It works out okay. So once it hits the ground, again, it presses, and I do a while true, so it'll just keep going down, 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 and then all of a sudden it touches, it goes back up and repositions. And that is pretty much the whole gist of the trigger switch I made for the interrupt. And of course I energize the magnet before I start my descent for the switch to be triggered. And that worked out actually pretty well. I do have, this is just a washer right here, small washer with tape, this blue tape on top of the magnet and underneath the washer to help insulate it a little bit more from the magnet. I didn't want any of the current from the magnet to affect the interrupt switch. And so as soon as this nut, which is touching this washer, which has a little pin back here for the other half of the interrupt circuit, touches this bar, the interrupt occurs and it stops its descent.
So I want to kind of go through what this project entailed in some detail. Here we have the robotic arm, and I've done quite a bit of modification to it. This robotic arm is the one I've been using for all my projects, and it's a little unique. I mean, there is a base servo, there's a gearbox servo here, there's an elbow servo, a wrist servo, and then what I call the gripper servo. I converted this gripper portion to this kind of longer arm that holds a pixy camera. And basically there's a MPU 6050 accelerometer gyro module here to level out the camera when I go to pick up something, using this down here, which is the electromagnet. It's a small electromagnet that picks up this little puck, and this puck is really, you can barely see right in here, large metal washers, and it's red so that the camera can see it. I have one that's blue and green, and they're just large washers. And what happens is the camera scans the surface of the table here in front of it, which is what this ruler is. You get kind of an idea how long this thing is too. It's about 14 inches long from the base, maybe longer than that. I look at it maybe 15 or 16 inches, so it's fairly long. And it scans the tabletop using the pixy camera, and when it detects this red object, it uses Inverse Kinematics to adjust all these servos from the start position, say up here, down. Let me draw a little bit here. From the start position up here, where it's scanning back and forth, all the way down to pick up this puck with the magnet. And there's a lot entailed in that. I thought it was going to be a lot easier to do this, but it actually was quite difficult. A lot of limitations on the servos, a lot of limitations on the motor. In fact, I don't know if you can actually see right here, but there's a switch I made that triggers an interrupt along this cable here back to the Arduino, so that as the arm comes down to pick up this puck using the electromagnet, it just continues to go down, and then it eventually touches here, creates an interrupt. The magnet is already energized, and by then, once it touches, it picks it up and then moves it somewhere else. So there's a lot going on here. It has to level out, it has to see it with the camera, it's got to pivot using the pan, it's got to reposition the arm using the arm servos and a gearbox. Some of the limitations I have that I should show you here is from here to the tabletop. This distance here is actually below the tabletop, and so my calculations don't take that into consideration. That's kind of a concern, and that's why I had a few problems. Another thing that I had that was a problem was this right here. I am using a gearbox versus a servo, and this gearbox 90 degrees for this, 90 degrees for this gearbox actually is at 65, and I'm writing like a child here because I'm not used to using the mouse. 65 degrees. So this is off. This is 90 degrees. It goes from 0 to 90 and everything, you know, or 0 to 180. This goes from, basically I got to be careful because it actually bottoms out on the base here. So I got to be careful. It can only go up to 65, which is straight up and down, and it goes down to about 30. So you're only talking 35 degrees of movement. There's an incredible amount of weight. By the time you add this onto the magnet and whatever little doodads I have out here, I had to add this extra spring right here. And that's a heavy-duty spring. I mean, considering, all things considering, it's a pretty heavy-duty spring. And it helps lift this portion of the arm up and relieves the gearbox of moving so slowly. In addition to that, there's tons of wires that come through here and down here. I had to buy an extension wire here for the Pixie camera because it has to go all the way back. You can see it right here, all the way back to the board. And, you know, you're talking 6 pins. There's a data pin, there's SCL, there's a bunch of stuff going on here. Control wires and power cables that power the Pixie camera. So there's a lot of wiring involved, and I didn't really address it. Initially what I did is I put it in a little plastic sleeve that kind of kept it all nice and tidy. But I found that as this arm moves around, these wires get tugged and pulled apart, and so I had to zip tie them here. But all in all, I got it nailed down. It was a lot of work. It's still not as accurate as I would like, but it works mostly the way I want it to. I don't think I can really get it to work much better without maybe spending more on more gearboxes or higher end servos. So all in all, I'm pleased with it, and it worked for me, but I was really pushing the limits of it. So let's go to the next slide, which is the breadboard. And this looks kind of like a mess, but I want to explain some of the things I have that I found that worked for me. First off, one thing that I liked a lot were these wings that you attach to your, I'm using a Mega here, an Arduino Mega, that you plug in, and then allows you to anchor these wires in nice and tight on both sides. And then you can still plug here in the board. So you actually have 2 wires per pinhole, which is kind of nice. I never used that, but I thought it was kind of nice to have. Something else I also have purchased was here is a 5-volt relay, which using a particular here's ground, but there's a common here, and then this is the power here, and the power from these batteries through this little connector here basically powers these 4C batteries energizes the magnet, and once the magnet is energized, it picks it up, the puck, which something I wanted to point out. It's hard to see right here. Right here, this little blue right here is, maybe I'll draw a line right there, is a heat sink. What I found was the magnet was getting hot, and as this energized the magnet would get hot, and I had to get a heat sink for it. So I'll show you where all the parts are. I'll go through the parts really quick also. Another thing I did was I ordered, draw this here, right here is it looks like a letter C. It's a separate power supply that I power using this cable. It plugs into a USB. I'm using an Apple charging plug to power it, but I have a separate power supply for my gearbox, because I found with the power supply, and I'll show you which one I bought, it was just too much. It was just not working right. I mean, already I think I'm at 8.5 volts, 5 amp, with all the motors picking up and servos and everything else. So I've solved a problem with the motors, with the gearbox not working. What would happen is the gearbox would slam the arm down into the table repeatedly. This way, this gearbox, somehow the sensor, when it was all powered through one power supply, a desktop power supply, did not work well. And so that's why I added this auxiliary power supply, and that seemed to correct the problem. So it's basically wired for the servos and the relay here, and there's an interrupt pin down here somewhere. And then there's an MPU 6050 module I use for leveling the camera, which connects over here on this side somewhere. And they all share common power and ground, except for the servo, the gearbox, which has its own power, but I think the ground is connected right here. So that is pretty much a thumbnail sketch of the hardware that I used. I use this LED here to activate when the relay is tripped and the magnet is energized. So let's come through and look at, here's the camera, the Pixy camera. It's a standard Pixy. It's the one they have out on the market now. They're kind of expensive. It's $69, but it was well worth it. I've used it a lot. I've banged it around quite a bit. It still takes a licking and keeps on ticking. I have replaced this lens. I have replacement lenses you can buy. I didn't include them because I haven't really used them yet, but they have different apertures. One's more like a fisheye, one's a close-up zoom. So what's nice is you can just replace the lens and get different effects. This is the magnet that I think I used. This one says 12 volt. I think mine was 5 volt. I tried to look at the magnet, but all the lettering is in Chinese and it's worn away, so I don't remember exactly which one I got, but it was like this one. I mean, it's almost identical. It has a little hole in the top for anchoring a screw, and that's where I anchored actually a nylon screw with a spring, and when the magnet touches the holder that's holding the magnet, it creates an interrupt, and I'll show that up close, or I should have shown that up close. This is the snap-on heatsink for the magnet, keeps it cooler. You definitely need one. That magnet gets really hot. This is the USB cable I use to use for the separate power supply for my gearbox. The separate power supplies I'll show you here in a second aren't very expensive, and you can use them to run separate servos or a group of servos, and then you just plug them in with these cables to different, like I said, I'm using an Apple charging module. I guess there's an iPad one that's a little bit more powerful. I'm just using an iPhone one, and it worked fine. I know some comments on my website have said not to do that or whatever. I've had no problem. Plus, you can buy them. They're inexpensive. I would use it if you have a chance. One thing I did have to buy a lot of were these cables here, because you need the extra distance to go from the top of the robotic arm servo, like the gripper or the wrist, all the way down over to the board. Plus, you have to give it a little extra room in case you need to whip the arm around and move it, manipulate it. So I bought a bunch of these cables, and they're not very expensive. This is the relay that I bought to trip the to turn the electromagnet on and off. It worked. It works great. I actually inadvertently bought one or two of them the wrong size, and they didn't work. So when I found one that actually was the right configuration, 5-volt, 1 channel, I went out and bought a 5-volt 8 channel, because I'm going to use these all the time now. Here are the wings I was telling you about. They're not expensive, and they plug right in. They work great, and I guess you can use them on a Mega or on an Arduino Uno. I think they work great. Somehow you can attach motors here. I don't know how to do all that. I haven't done that yet, but very little documentation, but all in all, works very nicely. This is the power supply that I bought. I bought basically it's 5 amp, 32 volt. I probably would have got there's a slightly larger one that is 8 amp, 50 volt. It's one step up from this. It's a couple bucks more. If I'd really, I might have wanted to get a little bit bigger one, but this is the minimum you want to get. It's not very expensive, and mine has worked great. I really like it, and it got good reviews. And I think I review this in another one of my videos. Here's the MPU 6050 gyro sensor module I use for leveling the camera as I go to pick stuff up. And it's not very expensive. Comes with these little connectors that allows you to connect it into a breadboard. I haven't mounted these yet. I use straight pins and just connect it straight on. But you can do whatever you want. You got to solder it though. But you only really, for what I needed, I only needed 4 pins. Here's the power supply. I think you get 2 of them, 2 pieces. Yes, 2 pieces, and they're 5 volt / 3.3 volt. There's a little switch. You can't see it here in the center. I don't really see it. Well, it's here somewhere. Right there. That allows you to switch it between the 2 voltages. I'm usually buying at 5 volt, and it works great. I really like these little things. Sometimes it overheats and shuts off. The USB cable plugs right in here, just like an Arduino, and then you got a nice little power supply. You can actually access 2 runs on your motherboard. It plugs right in. It's designed for a motherboard. I only use one side, so they're well worth it. And lastly, this is the 4C battery holder I use to energize the magnet. And that's pretty straightforward. I think I got this at AliExpress. So those are the 2 places I try to buy stuff from first, AliExpress and Banggood. Banggood primarily because they've been very good. I'm really very pleased with their service. And I mean, you got to grant they're across the world, so what do you expect? There's a language barrier, but all in all, they've been really good and very helpful. You can't really send stuff back, but sometimes they give you credit that you can apply to buy other things. So I highly recommend them. AliExpress, I haven't had any problems. I haven't bought that much stuff from them, though. So getting on to the code. Here we have the code. It's a lot of lines. I'm not going to go in depth on my notes. These are all the notes I always include at the beginning of my code, so that if anyone wants to find some of the websites I've went to, I include everything here. My code will be uploaded to Mediafire, and you can download it there, and you'll have all my notes I used to design this. You'll have all the code, and this video. So here, this is the notes. I have more to add here that talk about the IK. I was talking about IK, which is Inverse Kinematics, which allows you to start at a point and then set servo angles starting from somewhere out in space or out at a coordinate down to your base. And your base is technically at 0, 0. And let's say you want to reach a point out in space that is 7 inches out and 10 inches up. And that would be 7, 10. And then you would put those coordinates in, and depending on the length of your servo arms, I have a 6-inch gearbox servo arm and 2 4-inch elbow and wrist servo lengths. You could have indefinite number. I mean, you can have as many as you want. I only have 3, and then a gripper, which does the tilt for the camera. But through Inverse Kinematics, you can set those servos so that each one of those arms reaches at the right position to reach that position out in space from your starting 0, 0 base point, which is awesome. Because you never, I mean, if you put something out in a field or up on a shelf, how do you reach it? Well, you have to kind of know where it is. In order to do that, you need to use inverse kinematics and distance and that sort of thing to find out how to get to that item. Now, mine was just on the ground, on the tabletop, so I had one level easier. Everything starts out at basically 1 or 0, and then it's either out 10 inches, out 8 inches, out 7 inches, or 5 inches. So the Pixie camera could do that. But if you wanted to get something that was out in space, say up on a shelf, a ping pong ball, an orange ping pong ball that's up on a shelf, let's say, then you could use a pig module, calculate the distance, figure out how far away it is, and then use inverse kinematics to get to that ping pong ball using a camera or whatever. So that's the gist. And I did a video on inverse kinematics. There's a lot to it. My inverse kinematics is very simplified and would probably work for most people. It worked fine for me. I wish it worked better. I could have spent more time on it, but it was enough to get the concept down. So getting on with the code, I always have Pragma once, because what happens is as you load these, sometimes you load duplicate libraries, and Pragma once limits you to only loading a library once, and that way hopefully that eliminates a lot of the problems. So I load the SPI, the Pixie for the cameras, servos, of course, the wire, the I2C dev-H for the MPU 6050. Here's the MPU 6050 itself, and then some math library for doing some calculations. I create a Pixie for the camera. I create all my servos. Here they're numbered, how they're laid out. I create the MPU 6050 gyro. I set up some points for the camera for calculating distance. Here are my variables. I have a flag for turning on the pan, which is the base sweeping left and right to find the red object. And that pan on is worked in conjunction with the Pixie camera. It takes data from the camera, and as I get to a certain point on the Pixie camera, I then set this to false right here, and then it stops panning and it goes on to leveling and everything else. Once we found a block, that's for the camera. This is the block it looks for. These angle is for the IK calculations. These AX and GX are for the MPU 6050, finding the leveling of the module. I want to find out if the camera is centered, so I set it true there or false, depending on what I need to do. A loop counter for just counting number of times. That's another variable down below. I'll explain it. And then your pan target is equal to your X center, and that allows me to pan and get the exact center location of the object I'm trying to pick up. And that was really kind of tough. I actually go degree by degree because again, that's when something I mentioned earlier, my pan servo is not the greatest, and it's a little bit jittery, and if it moves left or right, it'll be enough by the time you get 14 inches out to where the magnet is. You lower that down, I'll miss that little red object. So, like I said, I could probably buy better servos at a much higher cost and eliminate a lot of problems, but I wanted to make do with what I had. So, anyway. Here I define pi because I use it for the IK variables. Shoulder length, like I said, was 6. Elbow length is 4. Wrist length is 4. This is all explained in my video on Inverse Kinematics. I would watch that to see how this works. I use the same robotic arm. Here I calculate slope and the hypotenuse. That's misspelled. That should be Hypoten. But anyway, so here I set up some variables. My target point here I was testing for. This is some testing information. When I wanted to kind of test it was my target X was 6 and my Y was 5, and my origin, my start point, X is 0, Y is 0. That's always the case. These two will always be 0. This will change, and my X points were always 1 because they were on the table, and then my Y point would change anywhere from about 4 or 5 out to about 12. As the robotic arm got closer to the base, it got kind of caught up on itself because it can't really bend that well. So I tend to keep this for my testing, 7 or was 5, then I moved it out to 7, not 7.5. These are different numbers, like 7, 5, 10, 6. There's no fractions. I just wanted to make note of what I've tested. Here I create these float variables ABC. These are the angles. And then I have a positive answer and a negative answer, and then I have angle ABC. There's 2 parts to angle A that you have to add together, so that's why there's a temp. The positive answer and negative answer for X and Y come from the quadratic equation because you have a plus or minus the square root of some value. So that's why you have 2 versions of positive and negative. I tended to use the negative version. The positive would dip down below the table. And again, you'll have to watch that Inverse Kinematics video I did, and this will all make sense. I use the same code. All right. I need an interrupt. Interrupts are dependent by board, and then interrupt number, and then which pins are supported. I think I used pin 5, or for interrupt 5, I used pin 8 on my Mega. So you have to, you set up the pin, and then you declare the interrupt in the actual attach or detach. Here's the interrupt pin. Like I said, right here is 8. Yeah, interrupt number 5, and then interrupt occurred, I say false, and you have to make it volatile because I change this inside what is called the ISR, the interrupt service routine. And if you want that value to get passed, you have to make it volatile so that it's passed between your main program and the service routine. Excuse me. So the service routine should be kept very, very small as possible. And I find that a lot of weird stuff happens if you try to run stuff in or around the service routine. So good luck on that. This has been very difficult to get to run smoothly. This is used for when the robotic arm comes down and the magnet touches the red puck, and it keeps going down until it makes a switch connection. It touches a connection, and then it stops, and then it lifts up a little bit with the red disc, metal disc. And then you can do something with the disc. You can put it in a box or put it on a shelf, wherever you want. So that's basically it there. So then we go into the setup. And here's the wire begin and serial begin. It's standard stuff. Here's the I2. This is all given. You initialize the I2 devices. I always thought this was clever code, where you you can print, make a comparison, and if it's true, it does this. If it's false, it does that. I always thought that was very cool and wanted to learn to do that more. So you might want to use that in the future. And I've mentioned that before, I believe. So here's the interrupt pin. Mine is a pull-up, and I needed to do that. And it checks for the pin going low, and that's down below on the attach. So I'll show you that. Here's my base pin, shoulder pin. Here's my electromagnet energize pin, and here's my switch to turn the electromagnetic magnet on and off. Oh, I'm sorry. Yeah, 13 is the LED. This is the LED right here. This is the LED. Indicates when the electromagnetic magnet is energized, which is just the green LED. And then this is the pin that actually trips the relay that throws the C batteries to energize the magnet. Here I attach all the servos. Okay, center is false. That's just for the camera. I initialize all the servos. I go to something called reset servos. And if we go reset servos down below, it just sets the initial position of the camera up high so it can look down at the table and start panning if it finds the red puck. We initialize the Pixie camera, and that's the end of setup. That's it. So now we move into the actual program loop. I say running so I know that we've started looking, something's happening, because sometimes this stuff takes a little while to get going. Here I start to do a loop looking for a pixie block using the Pixie camera. And I do it more than once because I find that it has to kind of get going and to see if it can find it. And once it finds it, it sets blocks to true. If there was an object in the viewer, then it says found block is true. And then we go into while pan on, which pan is true at this point. We go into pan. So let's go to pan. So here we go. Here we are at pan. And I have some information here. This may not be quite as up to date as it used to be. I've changed the pan a little bit, but for the most part, this is correct. There can be a block or object centered in the pan viewer, but it could be closer or farther away. Must zoom in and out for distance. The pan tilt routine just gets the block object centered in the screen, not the distance. The distance, X center equals 159 and Y center equals 99. So these are variables that are set up by Pixie. So what I do is I now say I'm in the pan, and while pan is on, you're going to keep doing the pan routine. And so basically what it's doing is it's trying to search for a block. It's searching left or right, and basically the red disk has to be in the viewer to begin with. I don't have it seeking yet. This pan is only used for getting the red disk centered in the viewer. If you want to find the red disk, you'll have to write code to search the tabletop, which is just a scan 180, scan minus 180. I didn't do all that because that takes a long time to get it to do that and then show you. Anyway, so what I do is I say serial print. Here it's pan target. The target is equal to pan target is equal to the distance set from the object. This will tell you how far you are from the center of the object. And the center that I'm looking for, the number I'm looking for, is a pan target between 198 and 200. And I print that out because sometimes it starts out at 306, sometimes it starts out at 20, and you want to see that it's getting closer to your pan target. So I initially had it set at 160, 180 range, but that was nowhere near accurate enough. It's too large. I eventually wrote a routine called in range, pan target 198 to 200. And in range says if this value is between these two numbers, then true. come back true. And I'll show you the in-range code down below. But just for now, understand how that works. And if it comes back true, then it says, oh, it was found. And now pan is false. And since we only do this while loop while the pan is true, while pan will be false here, it'll blow out of the while. So this is what stops the pan from actually working. However, if there's a problem, if pan target is greater than 200, our upper limit, then we subtract 1 and write it to the base. We read the current position, we subtract 1 from that position, and then we write it to the base. And so we basically go back 1 degree because we're too far out. Let's say we're at 202. We need to go back 2 units to get to 200. The same is true if pan target is under 198. We find the current position of the base pan, we add 1 to it, and then we now write that so that we get closer to the 198. And we keep doing this nonsense over and over until we get in range between those two numbers. We set pan to false, everything blows out, we're done with the pan. Okay? So let's go back up here. Sorry for I should open up this in a different window. That'd be so much cleaner. But we go back up here. So here's the pan. We just finished out the pan. Now what we do is the pan is done. We found it. And there's another component. There's a pixy block Y, and there's also a pixy block X. I'm using the dot Y for right now. And that is a value. That is that value is showing you down in the pan. Once the pan has centered between 198 and 200, that's the dot X version. This is the dot Y, and this will tell you if it is closer to the base or further away from the base. And basically position 12 is 12 inches out, position 11 is 11 inches out from the base, 10, 9, so on and so forth. This should say 8. I didn't put that in. Anyway, and so what I have done is using inverse kinematics, I have calculated what X, Y positions I need to be at or to give the routine in order to get to position 12. These are required for position 11. So once the pan has stopped and found the item, it will know what the Y position is. And let's say the Y position is out here at, let's say, 11. Okay, the Y will be between 25 and 47. Perfect. Then I know in order to get between 25 and 47, I need an X1 of 10 and a Y1 of 3. And that was those points I showed you above where you have an X1 and a Y1 and an X0 and a Y0. And X0 and Y0 are always going to be 0 because that's the base. That's where your base servo is mounted. Now, for whatever reason, I'm not sure how it calculates out or calibrates out even. Out on the tabletop, 11 inches away from the base, this position here, X1 10, Y1 3, or 10, 3, is where I need to pass this target point down to the routine for the inverse kinematics to move all the servos to get there. Okay, and position 7 and 6 I haven't calculated out yet. I started using these and I don't need to do it. It's too close to the base anyway. So that being said, you need now to take that XY coordinate, put it into the inverse kinematics, and it will move the robotic arm down to position, in this case, position 11. Now there's one tricky portion you need to keep in mind. If your target point, your x1, y1, that you see up here, is closer to the base than the length of your shoulder arm length, your shoulder servo. Let's say my shoulder servo has an arm length of 6, but if this point here, x1, y1, is within 5 inches of the base, you got a little bit of a problem because the shoulder base servo can't bend below 6. That's where I have a special calc point. Otherwise, you just calculate the point. If it's out there, 10 inches or 12 inches, you're fine. But at 6 inches and shorter, you got to handle it a special way, and I'll show you that. So once you have your XY and you determine which calculation you need to do, this is actually inverse kinematics calculation. You then run either the special calc point or the calc point. So let's go down to special calc point. Here's a special calc point. And what you do is you have to calculate the the hypotenuse, and then you calculate your angles, and you use inverse kinematics to calculate your angle A. This is what this is. Your angle B, your angle C, and then your final angle A here. We have to add different portions. My angle A is a little bit odd because remember I mentioned I'm using a gearbox servo that goes from 30 to 65, and that's a problem. So I have to make an adjustment here. I check to see if it is not a number. If it is a number, angle A is a valid number. If you try to divide by 0 and take the square root of a -1, it won't work. We print angle A, we move shoulder tilt servo to angle A, and so now we have angle A set. We do the same with angle B, all this, and this is just some debugging here. We then write that to the elbow tilt, angle B. Otherwise, if it's bigger, then we have to, if the angle is larger, if the current angle is larger than A, then we have to subtract. So it makes a little bit of difference which side of the angle you need to use. But if you look at the inverse kinematics video, it'll explain all this in detail. But nonetheless, you wind up writing that angle, angle B, and then you do the same thing for angle C, which is here, you write it here, and now you've written angle A, B, and C, and your servo, your camera head or magnet will be right above, basically right above that red puck that you want to pick up. Now, that's only if the red puck is closer than 6 inches. If it's out more than 6 inches, say 10 or 11 inches, we run calc point. And calc point, it's basically the same thing. You calculate the slope. You calculate these target circle A, B, and C lengths of the triangle. You need to calculate. You use the quadratic equation. This is just some notes to myself. And there's two portions. Once you use the quadratic equation, there's a negative portion and there's a positive portion. I didn't use the positive portion so much because technically the arm is cupping upwards and it will go through the table in order to cup upwards. So I typically always took the negative portion, which was leaning over or cupping over the target, the X1, Y1 target. And that's what this does. And so now we're above the red puck, and we go from calc point we call calc circle, which is right here. This is the positive portion, but there's also a negative portion where we call calc circle, and we pass our negative x answer and negative y answer that we generated from the quadratic equation. And we pass them in here, and we calculate the hypotenuse, the elbow length, the hypotenuse, the shoulder length, and then we calculate these angles. And from there, that generates your A angle and your B angle, just like above, and your C angle, and then writes them and prints them out. So that would be the calculate angle, or calculate point portion, in order to get the camera or magnet right above the red puck. This is a calc circle. Whoops, this is calc circle, which is the version of the special calc circle. Special calc circle, I was saying, the puck was within 6 inches. This is if it's 6 inches or further away, like 10 or 11 inches. So the two routines work really the same. They just handle a few things slightly different. And again, the inverse kinematics routine will explain how that works. So now you're above the puck, and you've made the right call to either, depending on what your values are up here, either special calc point or calculate point. And then they eventually both wind up calling, calc circle and moving the head and the magnet where it needs to be. So after that, if a block was found, we reset it to false so that we can do another search. We call pan. Again, I called pan up here, right here, but I call it a second time down here because sometimes as the arm moves around, it's a little, like I said, it's not very accurate. This allows me to run the pan again and get very, very close to the center of that red disc I want to pick up. And speaking of pick up, that's what I do here. I go to pick up next. So Control F. Let's see if we go to pick up, and once we go to pick up, there's a temporary hold of the current shoulder position. I write the shoulder to position 50, which is basically, it's hovering right above the puck. And sometimes it's close, sometimes it's far away, but I need to rotate that magnet into place. And the magnet's actually behind the camera. So what I do is I store the current shoulder position. I move the whole arm up out of the way. I then turn the magnet on, and then I level it. And when I level it, that brings the magnet level and ready to pick up the puck. So let's go to level. And here's level. This is all setting up the MPU 6050 module. I take the constraints and I set it into 0 to 180. While the position is not 90, keep doing this stuff over and over until you get 90 degrees level. And it goes through the same thing here. If it's greater than 90, I subtract a degree. If it's less than 90, I add one. If it is 90, I break, and I'm done, and I end level, and we're done. So that is part of that's the front half of pickup. So let's see, let's go back to pickup. Here's pickup. The magnet is on at this time, so it's energized. It's level, and then I rewrite shoulder tilt back to the temp hold position from up here, so it goes back down to where it was after the inverse kinematics. So it's back to its original position after the level. I level it one more time just to make sure, because now the magnet is out of the way and doesn't bump anything or disturb it. Because what was happening was the camera was scraping against the surface of the table because the magnet was behind, and sometimes it hangs down, and I didn't want that, so I moved it out of the way, level it up, bring it back down, level it one more time. And while this is true, I say interrupt occurred is false. So an interrupt has not happened yet. And I keep doing this forever, which is I attach the interrupt to the ISR. That's the routine that you run. Anytime there's a change, trigger this interrupt. And interrupt number was from up above, and this is interrupt number 5. And I found that sometimes it would return to here after the interrupt, so I'm not sure how that works really. If an interrupt occurred, we break. We get out of this while statement. Interrupt occurred is only set to true in the ISR. That's all it does. And let's go down. Here's the ISR. Interrupt occurred, true. I just say touch so that I know. I print the interrupt so that I know that it went from 0 to 1. So this goes from 0 to 1, because up here it's 0. And so every time this happens, anytime an interrupt occurs, it'll run this routine. It'll change this. This will become true. It'll break out of this forever while. And what we're doing is we're saying I equals I plus 1, looking. I print the I. And then the shoulder tilt right temp hold, which was from up here. This is where it came in from the inverse kinematics. That's where it finally stopped. Minus I, which is minus 1. And it'll start to decrement. It'll go down 1, 2, 3, 4, 5, until it eventually keeps hitting the table or keeps going. It'll go on indefinitely. Temp hold might be, let's say, 40 degrees. And the first time it'll subtract one will be 39. It'll go through 38, 37, 36, 35. So, because temp hold doesn't change. And eventually it'll hit the bottom of the table, and on top of the table, right below it, the magnet is energized, because I turn the magnet on right here. Whoop, dang it. Because I turn the magnet on here, and it's a pretty powerful magnet. Once you get even near that puck, it just sucks it right in. Make sure your batteries are good, but yes, it'll suck it right in. The magnet will hit the tabletop. It'll trigger the interrupt because of the switch I made, and I showed that, or I will show that. I then detach the interrupt so that it doesn't bang around or cause noise. This becomes true. It breaks here. It comes down here. It writes the shoulder to 50, and it kind of stops at 50 for me. I could have it call another routine where it goes and puts the puck somewhere in a box or a bucket. I turn the magnet off, and then the damn thing falls to the tabletop, so you got to catch it. The magnet on, that's basically, I showed you the ISR. That's basically everything. I'll show you the magnet on routine. Here we have magnet on. It energizes, it turns the LED on to show that magnet is on. You also hear a click when this goes true. And then magnet off is magnet. I say magnet off, and I turn the LED low or off, and then I release the relay, and the power releases, stops flowing to the magnet. Now, going back up here, there's reset servos. Let me show you reset servos really quick. Shoulder tilt is 65. That's almost vertical. It's 90 degrees almost. And the elbow, as long as it's less than 80, I cycle at 2 degrees. I move these servos slowly. I used to have them just go straight to a number, like 65 or like right to 80. I'd say elbow tilt right 80, and everything would just whip to that position. With all that weight at the end, it's not good. You get things whipping all around. So if the elbow is above 80 or below 80, I add 2 degrees, and I keep riding it until I get to 80. If it's below 80 or greater than 80, I subtract 2 degrees until I get to 80. And it's the same thing with the wrist. If it's not at 50, then I read the current value. As long as I is less than 51, I add 2 degrees, and here I subtract 2 degrees until I get to 50. And then I set the grip tilt to 10, and then if it's less than 11, I add 2. If it's more than 10, I subtract 2 until it gets to 10. And they slowly move into position. It's a much better way of moving the servos into a starting position, because you want to make sure it's at the same position each and every time. As a sidebar, this print info, I'm going to go ahead and show it since you see it here on the screen. This is just pixie information that I print out to keep an idea of anytime I need to take a snapshot of what the camera was looking at numerically or digitally as far as the numbers. This gave me my X position, my Y position, my X position, those centers, all sorts of stuff. So when you get the Pixie camera, if you get one, you'll understand this more. Here's the in range, and this is the last routine. I pass the value, and then I check the minimum value and the maximum value, and I return minimum value and maximum value. If it's true, then this returns true. Otherwise, if this is not true, it's false. So if the value is not the minimum is not less than or equal to the value, and the value is not, and the maximum is not equal to or greater than the value, then this will be false. But otherwise, it'll pass it true. So now let's go back up to the code. And I think this is basically the end of the code. There's really not a whole lot. I'm sorry about all this scrolling. I need to work on making it a little bit easier to see. So that's a level calc point. So basically, here we are back at the end of the loop. We did our pan, we did our pickup, we reset the servos. I just showed you how that works. I say pan is on is true because we're going to start another pan function. And fundamentally, that's it. That's the end of the loop. And it just goes over and over. It'll keep doing this loop over and over. And it will only do this block of code when a block is found, if blocks are true. If it isn't, it'll just say running, 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 and keep going. So that, in a nutshell, is the code for this robotic arm and all the features it runs. I hope that you find this video informative. It's as accurate as I can kind of get it. I think it probably needs a little bit more work, but it's done what I needed it to do, and I need to move on to some other projects, and I need to use the robotic arm for that. I want to get this out there because I have some unique stuff that I used with it that I thought that worked really well. And so I hope you enjoy this video. And if you do like it, leave comments. Don't email me. I can't respond to emails or anything. If you want to leave a question for other folks on the videos, that's fine. Maybe they'll respond. Maybe they won't. I'm just putting these out there for folks to use. You can download the code. All my notes are included. Please subscribe and like if you would. I'd appreciate that so I can keep doing these videos. Other than that, good luck.